Pharmacy and a PhD degree in Electronics from Indian Institute of Technology, New Delhi. He joined IBM Research India in 1998 and he is a member of the IBM Academy of Technology. I now request Dr. Subramaniam to start with the lecture and help us make our large data noise-free.
Thanks a lot. Can you hear me at the back? Okay, great. So I know this is the last session. Everyone will be, probably tired. So let's try to make this interesting and interactive as far as possible. Please ask me questions, interrupt me anytime you have a question. So as the title says, we are going to look at big data and we are going to look at the noise in the big data and how do you tackle this noise. Now as you will see as we go through this talk, you'll see that there are a lot of open problems, there are a lot of issues, and in fact the talks that you heard throughout the 3 days are all relevant in this case. And we'll see how that relevance is there in some cases. And so what is big data? So big data has been characterized by data which has 4 key characteristics. So one says that it is big data if it is high in volume, it is high in velocity, variety and veracity. Now of course typically, we've always dealt with big data. It's not that big data is something very new. For example, some of our banks, State Bank of India has 300 million customers. If you just look at the database of customers there, that's big. Similarly, you look at any of our telcos, the volume of their customers, the number of calls that they handle, that's all huge in volume. But often, big data is characterized by a new set of problems. And what we will talk about today are those new set of problems that people characterize big data with. So even though, State Bank of India might have 300 million customers, because that's stored in a database, databases are very well understood, people don't call that a big data problem. But as soon as you're talking about those same people making ATM transactions, making card swipes, now that becomes a big data problem because you're looking at data which is coming very fast, because a card swipe happens right now here outside in the mall somewhere. The bank wants to know and react to it immediately. So the time aspect, the variety of the data aspect, some of the the noisiness in the data, these are what is constituting what is being called big data. So we are specifically going to focus on the veracity aspect, which is data in doubt, data which has inconsistency, which has incompleteness, which has issues which we will start defining as we go along. So just to be, of course there is no hard and fast definition of big data. Big data today is defined as a term that applies to information that can't be processed or analyzed using traditional processes or tools. So that's a very relative term. What is traditional, what is known, what is unknown, what is big data. So these are all because this is an evolving field, because the problems here are evolving, the definition is also a very relative definition to what was there before to what is there today. Okay? And but some of the attributes of this data include, when you're talking about card swipes, somebody is swiping a card. There are millions of card swipes happening every second. For example, from Visa or MasterCard or American Express or any of these. And for each of them, this volume is, the data is very high in volume. It is structured, of course, but it has a high throughput, So there are, social data has other issues, it has high variety, there is text data, there is image data, there is video data there, and it is highly unstructured. Again, that data is coming very fast. There are 55 million tweets that get produced every day. Right? And this data is only growing, right? So this data challenge that we are seeing today is growing exponentially. The companies that are handling this data like Google, Facebook, they are handling terabytes of data which is getting generated almost every day, right? And this data, 2010 we are there around that 10 exabyte mark, and that's growing exponentially. And the challenge is that a lot of this data is also uncertain in nature. There are veracity issues with this data, and we'll try to see what these are. Now, traditional data processing has been here in this pink space, right? So what does that mean? That is, traditional data processing has limited itself to data which has volume, velocity and variety to some extent. And there is uncertainty to some extent. So, for example, in a structured database, when you're saying that give me all records of people in Kolkata, when you run an SQL query on a database, all the results that get returned, you can assume that that's a closed space. You can assume that whatever has been returned are people from Kolkata, and whatever has not been returned are people who are not from Kolkata. Why can you assume that? Any ideas on why a relational database you can make such closed world assumptions on that?
Because the data is finite.
Yes, the data is finite, it's structured, it has attributes which are very well defined. Those attributes can only take on some definite set of values, a finite set of values. Now, let me assume that I now go on Twitter and start to mine people who are from Kolkata. Okay? So, as you know, on Twitter, not everyone writes their location information in the profile, right? Some people might write Kolkata, some people might write Howrah, some people might write ISI, some people might write Moon, some people might write Cloud9, some people might write Bathroom. People on the social media, that attribute, location, can take on an infinite number of values based on the creativity of people on Twitter. Now, if you were to mine information from Twitter and populate a structured database, still it does not conform to the closed world assumptions that we have. Why? And in fact, there are trust issues. Even people it says are from Kolkata might not be from Kolkata. Because there is nobody verifying it, there is no editing of this data. So there are a lot of issues at different levels in terms of how this data can be handled, how this data can be mined. Even the previous talk, which was about clustering, classification, all of those questions also take new forms. Just because this data is no longer conforming to some set patterns that we assume that data follows. But that's not stopping us from having applications which sit on top of this uncertain data, which sit on top of this high volume, high velocity, high variety data, and you're seeing these new applications coming up. Things like social network analysis for commerce and retail. For example, text, audio and video analysis for homeland security. So for example, our intelligence bureau would be mining certain calls, it would be doing certain things, right? Now, of course, how accurate are those transcriptions, how accurate are those things? They are all still at a stage where the accuracy levels are very, very low, but still the applications, it's not stopping people from having these sort of applications. Now, of course, everyone knows this. The social media is growing exponentially. In India, the number of users are growing very, very fast. And what this is meaning is that social media analytics is also taking off. Because, for example, if you look at the Delhi elections now, Kejriwal, his election campaign to a large extent was run on social media. And he and his team were monitoring the social media. Veracity arises from different processes. One is there is a process uncertainty. If I ask you how much time will it take for me from ISI to the airport, you'll say maybe 20 minutes, maybe 30 minutes, maybe 40 minutes. You'll give me a range, right? So there is uncertainty in that process. There is a randomness associated with this process. Then there is data uncertainty because of spelling mistakes, because of grammar mistakes, because of ambiguity, because of people deliberately spreading false information, because of conflicting data. All of these, because of these pieces of information, there is data uncertainty. Now remember, when SBI, we took the example of SBI, right? It has 300 million customers. So there is a name, there is an address, there is how much balance this account has. You can believe that to a large extent, right? That's the way the whole SBI business runs. When you go and say, give me 10,000 rupees, I want to withdraw 10,000. If they see that you have above 10,000 in the account, they give you that money. It's based on the fact that that data is trusted. But can you say the same thing about social media? Now, I might have a friend, let's say Partha is my friend. I might believe everything he says. So if he tells me that there was that maybe the Chief Minister is going to visit ISI campus tomorrow, I'm going to say, okay, maybe with 95% confidence, she's going to visit the campus tomorrow. But I trust him, but still he could say, maybe she will visit tomorrow. So even with that trusted source, several levels of complexity get added because of spelling mistakes, because of the ambiguity, because of the trust associated with the person who is sharing that message, because of the trust or the confidence of that person who is sharing that message. Due to each of these aspects, there is an uncertainty that is creeping into this field. And that's why when we say that all of this big data is uncertain, that's what it means. It means that all of this social media data, all of this data on the web, it has several challenges in terms of how do you make use of that data, because it's not trusted, because it's not you're not confident about what is there. And finally, there is also modeling uncertainty. So we all know when we try to fit a model, it does an approximation of the data points, right? So that model is trying to approximate the data point as it is given. This is how clustering works. This is how classification works. All of our machine learning, NLP techniques, a lot of these work based on these models. But there is always a modeling uncertainty. You measure it based on maybe the accuracy. You say that, okay, my model is 80% correct, my model is 90% correct. Now, this same thing, if I build my classifier based on Times of India data and start using it on Twitter data, model which I built for very perfect edited text from Times of India is not going to work for the social media. often, these are some of the challenges we face and we talk about some of these. So, are there any questions? So, what is noise? Now, we'll limit ourselves to just text. Yeah.
My question is, right now we're talking about veracity. So is it actually a problem or some sort of gift? Because what I feel is there is no need of so much of accuracy on social network. So what is it actually a problem? I mean,
yeah. So I'll tell you about applications. We'll go to those later on, and we'll see why we need to be accurate. I mean, of course, there are applications where you don't need to be accurate. There you probably don't care about how well you are able to understand. But there are other applications where you do want to understand. So we'll talk about some of those as we go. So all of this is human generated text on social media or even on the SBI relational databases. A lot of that. I mean, of course, some of that is machine generated. When you swipe a card, that's a machine generated swipe. But when you fill the form saying that this is my name, this is my location, this is my address, I want to deposit 500 rupees to open my account, all of that is human generated content. You fill up a form when you're trying to open an account, and that's digitized and stored in the SBI account, and that's where the relational database, you're one of those 300 million customers of SBI. Now, some of this is human oriented, some of it is electronic. Of course, a lot of it is human oriented, but some of this is paper documents, some of it is audio speech. So there you have a lot of the modeling noise. Your speech recognizer, if the accuracy is 60%, then that is introducing errors into the transcription process. Right? Similarly, SMS, online chat, Twitter, Facebook, that's electronic, but because it's informal conversations between people, so again it has challenges when you try to machine read it and try to infer using a computer program. So just to give you a feel for what this is, newswire text, the error rate there is 0.0005%. So the previous talk, when the person was talking about Reuters data set, 20 news groups, all of that is newswire data. The text there is perfect. Somebody with very good English, with excellent knowledge of grammar and spelling and everything has written that. When you read Times of India, you're not going to find too many mistakes there. So that's the quality of newswire text, 0.005%. You look at OCR technology today, 95 to 96, 97% on well written electronic text. Web queries, things we type on Google, are queries. Before I came here, I checked out ISI Kolkata. So there, in those queries, 2, 3, 4 words maximum, people make about 15% error in terms of spelling. And that's why Google has this, did you mean this? It tries to correct your spelling or query that you typed in. Automatic speech recognition, about 30%. You can go up to 50% if you're on a phone line or if you're not a native speaker. So if I start speaking Bengali, there is a speech recognition system trained on Bengali speech, it's going to make a lot of errors. Maybe it's going to achieve 20% accuracy. And then you're coming closer to social media SMS. Surprisingly, you're looking at half the text being You and I can make sense of it, but when you try to make a computer read that text, make sense of it, there are challenges, right? So as soon as we all know how people write that, right? So the kind of noise we're looking at, deletion of characters, phonetic substitution, uh, abbreviations, dialectical usage, deletion of words. People make all sorts of, and these are surface form mistakes. People make a lot of grammatical mistakes. They mix languages. They mix Hindi, Bengali, English, all of this. And that's why on social media you're seeing that the error rates. If you look at a piece of text, out of 10 words, half of them are not real English or real Bengali or whatever. Speech recognition, 10 to 40% error, that's the way it looks. Right? A speech recognized text looks like that. When we are speaking, say, full stop, comma, that's why you don't see any full stops there. You run this text through parts of speech, parsing, any of that, it's going to give you a lot of errors. Because parts of speech assumes that there are full stops at the end of every sentence. Okay, so things that work very well on that newswire text, all of text mining, all of classification, clustering, machine learning today is based on those very well formed corpora. That's what we use typically, to build our systems, to build these machine learning systems. If you go and look for a Twitter data set, you're not going to find a Twitter data set for doing parts of speech. So as soon as you take a parts of speech tagger which has been built on Wall Street Journal or whatever, well-formed English or well-formed Bengali, and bring that and start using it on social media text, it's going to fail because of there being very simple things, not even spelling mistakes, not even grammar, just because there are no full stops. The accuracy of that parts of speech tagger will go down from 90%, down half, it's going to go to 45% or even lower. Historical text, I don't know how many of you know, but Shakespeare's time there were no dictionaries. If you read Shakespeare in his original form, for the same word he would have used 10, 15 different spellings. Which is very similar to what we do on Twitter today. We use, different spellings for the same word. I might want to say Kolkata and I won't care what spelling I'm writing, I'll just write some KOL or KKTA or whatever, and every time I'll write a new spelling for Kolkata. And that's exactly what Shakespeare did, In his original writings, if you look at his, words there, for the same word he would have used many different, often as many as 18 to 20 different spellings for the same word. Of course, they did it for different reasons. They wanted to, for example, if the word was going into the next line, they would drop some of the words there. They would do all sorts of manipulation because the editing or the printing that time was also not very advanced. Today we have Word, which does all those things, but at that time it did not do. So a lot of the spelling mistakes were done because of that. Today the spelling mistakes are done because we are using these very small keypads, mobile phones, because we want to appear cool to our friends, because we want to type quickly, we don't have time, because there is a character limit, 140 characters on Twitter, SMS and everywhere else. So for all these reasons, we are going back to that stage where there is a dictionary now, but people are not using those dictionary words in these informal communications that they are doing with their friends and everyone else on social media. blogs, chat, and we all know that the quality is not very good there. So what is noisy text? So some definitions have been tried, and one such definition is that this is any kind of difference in the surface form of an electronic text from what was intended, what is correct, or the original. Now you can see this is a very broad definition because it's trying to capture all kinds of noise, but it still doesn't capture all the types of noise. It's only capturing the surface form noises really. It's not capturing syntactic and all those forms of noise. So noise can be at several levels. It can be at the lexical level. Before can be written in multiple ways. It can be at the morphological, syntactic, or discourse level. I can hear you, I can hear you, I can hear you. Three different ways of writing it. Only one of them is correct. But of course, we still write all of these. Now, how do you classify noise? Again, there aren't too many works that say how do you classify noise. There have been some attempt, for example, lexical errors, people talk about missing characters, extra characters, phonetic substitutions, abbreviations. Syntactical errors, people talk about missing words, extra words, agreement, dialectical usage, different things. This is all coming from English and the way grammar is supposed to be, not only English, in any language that you take. Now, how do you correct these pieces of text? Right? So, of course, we all know there are several ways in which we correct text. For lexical errors, we look at n-grams, we look at edit distance, various kinds of ways in which we try to correct errors. Of course, they're all based on some sort of dictionary or on some sort of canonicalization of the erroneous forms. Similarly, there are things to detect incorrect grammar, syntax. Microsoft Word does it. You try to type something, if it thinks it's wrong, then it tries to correct it. Right? So how is it correcting you? It's based on marking, based on n-grams, based on some sort of a grammar which is there in that system. It's trying to compare what you're writing against that grammar. Of course, it could be probabilistic, it could be rule-based. All of those are there in different settings, and each of them have their own accuracy. Right? Now, now you can go to any depth. You will still see papers today which are talking about these things, because these are not solved problems. People are still trying to solve these. You can bring all sorts of errors and you can try to fix them. None of these are very scalable. They don't scale to big data scale. None of them is very fast, for example. They are all very slow methods, fast parts of speech, parsing. N-gram is relatively fast, but several of the other techniques are much, much slower. So they do not scale to big data scale. So how do you quantify this? Now, there is no single way in which you can quantify. Now, and that's because there are several forms of noise. So there is no single noise form, so there is no single way of quantifying. So things like edit distance, perplexity, word error rate, the blue metric, all of these have been used in different settings. And of course, for example, if I ask you to write a sentence, two people write it, they aren't going to agree in all the things. So there is always a disagreement between humans itself. So that when you try to impart some of that into a machine, you're going to see even more challenges because of that disagreement coming. So, the correction literature has, it started in 92 or even earlier. Before that, people have talked about different ways in which you can correct the text. Earlier, they all focused on very small errors. You instead of Kolkata, Kolkata, you write Kolkata. So you're talking about small edit distances, small errors in the text. And that's what typically text processing engines can correct. So if you look at even Google, Microsoft Doc, that can correct if you make small errors. If you make a lot of words, put them in error, it's going to. But that's the kind of corruption that you see in SMS, Twitter, right? Now this is from actual SMS messages that were sent to a call center. And these are, multiple in which people have written down. And as you can see, the correct spelling has been said 24 times. The incorrect spelling TOMOZ is more popular than the correct spelling tomorrow. Right? So, all our models are based on the premise that the correct is always going to be the predominant feature. That's no longer true. The correct spelling is no longer the predominant spelling on social media. I mean, it's there for several words, but there are several